Okay, so we will continue our discussion on boosting. In fact, in the last class, I just started these topics. So as we discussed that in boosting, the idea is that you generate a set of learners, and each complementary to from others. Right? Um, so we call them base learners, and complementary in the sense that they are capturing certain characteristics of data and based on which the decision is taken. So you can get uh, different kinds of decisions, and then you can use them. Or in other way, sometimes it's a kind of you are trying to segment the or you are trying to prioritize the decision making process in a hierarchy. That means easier samples are taking decisions by some of them, and only for the difficult samples then you consider the decision of the of a classifier which may be of higher complexity. Now, of a learner of higher complexity. So the example, particularly the first boosting algorithms, it has given some nice typical flavor of this approach, where we'll be considering, as you can see, that it is trying to find out that previous learners, what are the mistakes, means what are the incorrect decisions the previous learners took. And then for those samples, it tries to design some of the other classifiers where it would be. I mean, once again, it is trained with a different model with different parameters, etc., to check whether it can be also learned, and you take the decision based on that. Only problem is that during training, things are smooth because you know that these are the mistaken samples, and so incorrected classify wrong classifications, and you give it to the next stage. Testing stage, you have to make a policy that when actually you will go for this kind of when you should ignore the decisions of the learners in this pipeline in the beginning stage of the beginning. So when you ignore, then only you can go for the next stage. So some kind of characterization is required, or some kind of policy is required. So we'll see that how these policies are made by this example. The advantage of boosting, as you can see, that against bagging, bagging is simply you are randomly choosing your either your hyperparameters or your training sets, and then you are defining different models, and then you are trying to you are assuming that the consistent results will come from the majority. But no, there could be some instability of the training algorithms also there. So many of the weak learners, the problem is that some of the learners may be very weak training. There are inherent limitations of training algorithms also. So that still remains over across all the learners, because you are using the same learning approach mostly in bagging. In boosting, you can have complementary learning. That means you can have different learners also. So usually it is a weak learner set of weak learners combined together. They give you improve the accuracy. So this algorithm, which we discussed also in the last class, it's a combination of 3 weak learners. And what we do that we divide the input space training samples into 3 sets, and we correspondingly, we train different classifiers, 3 classifiers. The first classifier on X1, but we test it with X2, and then whatever misclassified samples are there in X2. Now those are used. Those are used for for training in the classifier D2, and then you test it on X3, and you check that what is the agreement between these 2 classifiers. Only those samples which are not agreed by them, now again use them for training the training the last classifier, which is kind of a acting like a the chairperson of a parliamentary committee or of a parliament itself. So like no, if the for any motion, if there is equal divisions, I mean for each, then the chairperson's vote counts. No? So similarly, it acts like that. The third one is like that. So we'll see that in the testing, actually we follow this policy. So this is what I was mentioning, that you train D1 with X1, test D1 with X2. So D1 is the classifier, first classifier. And then you find out the training set X2 prime for D2, which are not properly classified by D1, right? So misclassified it. And then again, you train D2 with X2 prime and test with X3. Sorry, test with X3 with both D1 and D2. And if there are agreements, then you know that no, it is consistent. Otherwise, you form a training set once again for a classifier, third classifier D3, which are not agreed by between D1 and D2, and you go for doing it. You only see that in this case, you are not checking whether they are correctly classified or not, only when they are agreed or disagreed, right? If both agreement may also lead to incorrect classification, you should note that, but no, we are accepting it. We are accepting it because no, the policy has to be consistent during the testing stage. Now, this is the first algorithm, but the more popular algorithm, which is used particularly for for this case, for the case of boosting, is that this algorithm is known as adaptive boosting, or in short form AdaBoost, is a very popular algorithm. So what it does, instead of partitioning the training set as we considered in the previous approach, you use the same training set over and over. But what you do, you randomly sample the training set to train a classifier. And during the sampling process, you will find that when you train a classifier, you know that some of the samples are correctly classified and some of them are not correctly classified. So which means that those are correctly classified, we are considering they are easier to classify, and those are not correctly classified, they're difficult to classify. So the sampling process is such that there is it's a random sampling, so there is a probability associated with a sample to be selected in the sampling set. Now, of a training instance to be selected on the sampling. Now, this probability is decreased as it is getting more and more correctly classified, and this probability naturally will decrease, means the and the probability start with I'm sorry, start with uniform probability and for all the samples, but no, you decrease the probabilities, and of course you have to normalize at each iteration. By this process, the later stages of classifiers are subjected to more difficult samples, and also you give weights. So weights to those classifiers which are handling more difficult samples, more weights. So there is a weightage scheme. So you are also determining the weights, and these weights are determined by the performance of the classifier. So if the performance is good, you know that it is basically kind of inversely proportional to that performance. So we'll see that. So let us consider this, that your training set need not be large for first thing. That means, as you can see, sampling it. So classifiers should be simple so that they do not overfit. That is another thing. That is, the model should be simple, and each should perform with an error rate less than half. That means they should marginally be better than the random guess. Random guess is that 50%. If you there are 2+ problem, if you randomly guess, your performance should be 50% chance that it is correct. Now it should be marginally better than the random guess. So with this, you combine an arbitrary number of base learners, not just 3, as I have mentioned, and there are many variants, and I will discuss one such approach which I just outlined. I gave you more concrete steps. And as I mentioned, randomly you are drawing samples to form training set, and if the sample is easier to classify, the probability of sampling would be smaller. So this I have already mentioned. So let us see how in the algorithmic form, in the computational steps, we are implementing these principles. So you note that here what we are doing, that at each iteration, we are training the sample set, and we are computing the training error E of classification. It is error, you just note, it is not the other thing, it is not the accuracy, it is just the error of classification, percentage of samples which are misclassified. So if this error is greater than half, then you should stop, which means it is too difficult. Those samples are too difficult to classify, so we are not going to handle it. And your approach may have also limitations to handle that. So we are stopping it. Either you modify the algorithm, or maybe you have to increase a little bit of your model complexity, because you have to start with simple. So simple means the next degree of complexity you may consider. I mean, if you do not have any classifier, otherwise, since if you have multiple number of classifiers, naturally you have to stop at some point. So this is a stopping criteria. Now, otherwise, if your classifier is marginally better than the random guess, as I mentioned, greater than half, it may be marginally, it may be also strong. So it does not put any restriction there. So what we should consider, that model is included in the list. But now we have to find out a weight of this model. Now this weight is computed with a, as you know, this weight is used for both reducing the probability of sampling for correctly classified samples of that classifier by that classifier, and also it determines the weight of the decision. So this weight is computed in this way. As you can see that weight is E by 1 minus E. So since E is greater than half, so this weight is high when weight is high for the classifier. But the fact is that for decision fusion, it is the inverse of the weight is used. That means, as I mentioned, that easier the classifier, less is the weight. But no, inverse is not direct inverse, is logarithm of the inverse we'll see in the algorithm. So there are all, these are empirically decided, and also there may be certain other reasons, so which I'm not aware of here at this right now, but you can read the original paper and can see the details. But intuitively, the weight of the decision would be the inverse to this particular factor, because this factor is greater than 1. You can see that. But on the other hand, the probability of the sample, I'm sorry, this weight should be less than 1. No? E is less than half. I'm sorry, this weight is less than 1. This weight is less than 1. So we are giving, okay, so weights are, sorry. So yes, so we are giving more weights to the easier classifier. So, yes. But we are giving less probability to the easy sample, easier sample for classifications. So please note there is a confusion in my description also. Just let me point out. This factor is actually, it is greater than 1. Okay, this factor is greater, because E is here, it is else clause. E is less than half. So naturally, this factor will be greater than 1. Now, since it is sorry, if it is less than 1. Okay. Yes, E is less than half, so this factor should be less than 1. So in this case, this probability is getting reduced. You see that probability of classified, because you are multiplying the fraction with this probability, which is less than 1. So this probability, after updated, this probability gets reduced. So in the next stage, probability of sampling would be, of sampling this particular correctly classified instance would be less. And you have to normalize it. As you see that you are doing it for every samples, but some of their probabilities has to be equal to 1. So you should normalize it after this. So that step is also there. So that step also has to be considered. And the weights are determined in this way. So as I mentioned, the normalized probabilities of samples at each iteration, and you are taking the logarithmic of 1 by Wi as the weight of the decision. So which means that you are giving increasing weight to the decisions for easier classifier. That means classifiers which are at the beginning of this, not easier, but for which has good performance, I should say. Not easier, not that the classifier which are having good performance, you are giving more to. Yes, that is more intuitively right reasoning, that the good classifiers should be given more weight. So good classifier means who have smaller e, who have smaller e, and that's why their value of 1 by Wi should be high for them. So it is these weights are taken in this form. So when we go for the decision fusion, that it is the weighted sum of this decision fusion. So in the same way, the way we have discussed earlier, how the decision fusion takes place when there are multiple classifiers, L classifiers, and if there are K classes. So for each class, you are getting a value. So djx is the value for that particular class, for the sample for the for the say ith class, that you have to consider. I think that that is the understanding that should be there, and which means I have to also use the subscript I in that case, just to denote that it's a decision for the ith class. For each learner, it will produce that, and then you are making the score. You are making the weighted sum of the score, and you are assigning the class with the maximum y, something like similar to map approach, where even this score could be the posterior probability of the class posterior probability from the classifier, but it could be another score which have some, which is similar kind of thing. And increasing the score means more probable is that you are trying to assign that sample to the class. So you are assigning the class with the maximum y. So this is what is your this approach, AdaBoost approach, and you are using simple classifier so that error is not low, and decision tree grown up. Some examples like you can use decision tree with small number of levels, so that is a simplicity. I mean, if you have the larger depths, means more complex. So we call them also sometimes decision stump. And it is just to note that linear discriminant classifiers are not very useful because they have low variance among among these set of learners. So most likely they will be behaving similarly. As I've already mentioned, that there has to be some complementary in nature of the learners. But this particular linear discriminant classifiers, somehow they behave, they have a low variance that is observed. I think theoretically also that can be shown. Now, this is the approach, like we have considered the approach of bagging, then the approach of boosting. The third approach, where we would consider the mixture of experts, which means there are certain experts for certain domains. And if you can identify the input sample drawn from which domain, you will be selectively choosing that expert to take a decision. So let us see what kind of different approaches are there. We'll see that there is an approach, cascading approach we'll be considering here. So we'll find out. So, basically, you can have certain certain order of experts. That means if the first expert fails, then it refers to second expert, something like that. So again, also something like you can say that some priority is there. Some experts are also put into certain order. They have been given certain power as they act in that way. So in this case, in voting, weights are fixed for each classifier And in mixture of experts, depending upon inputs, these weights would vary. So that is the that is the principle. As you have seen that in AdaBoost also, or any decision fusion, um, every classifier has its own weight and which is fixed. But when we are saying mixture of experts, now depending upon the input characteristics, each expert will have certain amount of confidence to take a decision. You know, like nowadays in reviewing various proposals, one field is asked that what is the confidence by which you are examining it, and the examiner has to give a confidence score there. I mean, supposed to give us confidence score there. So this is something like that. So you are the experts. They are not only giving a decision, they are also giving a confidence score, and by from that score, the system takes a no has the liberty to choose what in what way they will makes this they will make the decision fusion. Like those confidence score can act as the weights of the experts. So ideally, uh, this score should be close to 1 if there are local experts, and 0 for others if there are local experts. But as you can see that this locality may not be very well defined. So this is also called voting by gating systems. That means you are allowing some of the experts votes only, not the others. And final classification score for each class is the weighted means of votes. That means even if you, from your panel of experts, for a sample, you are only allowing a few experts to make a decision, and then you are considering decision fusion from there. So this method, this stacked generalization, in this method, what we do that instead of a linear combinations, the way we have seen for the weighted average, we can even consider that these are the input vectors. And so these are the decisions from different learners, which are supposed to be experts in my context. And then you know what is the correct decision in a level data set. So why don't you consider this is also an input to the decision fusion process, which also has to be learned through some classifier. So it is the second stage of classification. In the first stage, you take the decisions of experts, and in the second stage, you use another classifier where you learn how to best use of that decisions to get a correct classifications. So in this way, you are doing it. So it could be a multi-layer perceptron. So that is one kind of strategy, that is the stack generalization strategy. The cascading strategy is the one where you are basically uh, defining a pipeline of experts. So if one first expert fails, then that means the confidence is low. Then you go for the second expert. Again, if the confidence is low, then you go for the third expert. Moment you find a confident decision, you stop there. So this is kind of the approach is a cascading decision. So in this case, as you can see that base learners, they are ordered in terms of complexity. So we are assuming that more complex is a model, it would be that would be for the more expert, but the catch is that it should not overfit. We are always trying to, that is the principle of that parsimony principle, that we have already considered that just missing the term. So there is a principle by which you should always look for simpler classifier. That should be preferred. So preference is for simpler classifier. But if it fails, then you go for the more complex classifier. That's why the models are put into a pipeline of making decisions in terms of order of more the complex model, later it would come into that pipeline for the decision making process. Later would be it is used. So each learner produces output with a confidence, and as you can see that D1 is less costly than D2 and so on. So that is meant by these terms of complexity. And when you are producing an output Y, you are also giving a confidence. So WJ is confidence of decision for DJ, for example. DJ is the Jth expert or Jth model. And I mentioned this confidence could be also a posterior probability, for example. So this pipeline can be expressed, the flow of the decision-making process can be simply captured in this way that suppose you get the input sample X and then you apply the learner D1, then you get the corresponding decision Y and also the confidence W1. Now, if it is sufficient, so if it is greater than certain threshold, you accept it and you stop it there. Otherwise, you go for the next best learner, used the previous learners, this is lack confidence. So you go for the next best learner and continue this process. That means you feed the model, the input, you test the input sample with that learner, check what is the decision, and you go on doing these things. So go on doing these things, and of course you have a finite number of experts. So finally, you have to choose a decision, or you can also ignore a decision if it is not of sufficient confidence. So so this is what is the cascading approach. I think more or less we have discussed about uh, different policies of um, aggregating the decisions of a set of learners, or which is called ensemble learning process. And you can see that as a summary that no learner is perfect, and we should consider in this case when we are considering a set of learners as an ensemble learning process, we'll try to keep the learners simple, and also the learners should be complementary to each other. It should be diverse set of learners should be there, and there are different ways this diversity could be introduced that we have also discussed. Now, for decision for fusion, we considered different rules like voting, and there are decision combination rules also we have discussed. Error correcting output codes is an interesting concept where you make the decision making process more robust with the multiple learners. So it is something like the stacked generalizations what we discussed, uh, but in this case the codes are encoding are given for a particular class in such a way that two classes they will have sufficient distance maintained in the encoding process. So if there is any error in the code itself, as a certain learner makes a mistake, still it can be corrected. Still you can take the correct decision. So that is the idea there. Of course, there are redundancies, etc. Other issues are there, uh, but this is also another robust way of taking decision. And then the approaches, some of the approaches for ensemble learning, like bagging, which means bootstrap aggregating, where you randomly sample the input space, training sets, and use the same learner. And of course, by varying, you may vary the hyperparameters also on the same training set. And you take different decisions, but assuming that the consistent decision will be coming from the majority. So from there, you take a decision. And then boosting method also you have discussed, where you are learning the complementary based learners and providing weights to the decision making process. There are other strategies of acting like a resolver when there is a there is a tie breaking rules of in a in a set of learners. A tiebreaker can be introduced when there is a tie. So that is also we have seen in the boosting approach. And AdaBoost algorithm we have considered. No? We have just discussed that how the weights are determined for each learner. So better the performance, higher the weight for a learner. So that is the policy. And for choosing the more complex samples in AdaBoost, they have adopted this nice approach of sampling from the training set, and the sampling probability gets reduced as and when it is getting more and more or easier to classify, and then it is getting reduced. Mixture of experts we have considered, and the stack generalization, cascading, which is basically following those concepts. So with this, I think we come to the end of this particular topic. So if you have any questions, let me know. So As I mentioned that that your last quiz will be on 18th November. That is on Thursday. So next week also we'll have classes, and um, next week and also the week after. So we have 2 more weeks to go. So I will start with the next topic, and which will be reinforcement learning. So thank you very much. So today let us stop here.